Yes, sir.
So we had talked about we had talked about this thing. This was Bohr's order of reaction. Okay, so I told you that rate of reaction depends on the concentration of the reactants. Like if you've got two things reacting, bumping into each other, so it depends on the concentration of reactant 1 and reactant number 2. And order is the power that determines how it depends on that. Like we know that rate depends on the concentration of X, but we don't know, like if you increase the concentration of X, the rate of reaction would speed up probably. But how does it speed up? So there are three orders. There's order 0, which means that it's not dependent on X. There's order 1, which means that it's directly proportional. You increase concentration, the rate also increases proportionally. And then you've got order 2, which means that if you increase the concentration, the rate would be, it's going to be a quadratic relationship, which is that if you double the concentration, the rate quadruples. If you triple the concentration, the rate becomes 9 times. If the concentration becomes half of the original concentration, the rate becomes 1/4. So we talked about that, and we talked about the mechanism. I told you that anything that's involved in the fast step, any reactant that's involved in the fast step will have 0 order, which means the rate would not be dependent on the fast step. If you increase the concentration of your reactant in the fast step will speed up, but it will have absolutely little effect on the overall speed of the reaction. Everything depends on the slow step. So it depends, rate of the reaction depends on the reactants that are involved in the slow step. You increase their concentration, the slow step speeds up, and that all of a sudden speeds up the whole reaction. So everything is dependent on the slow step. Anything that's in the slow step that has order 1. Anything that's in the fast step that has order 0. Then we talked about how did we get order 2? TK, we did all that working as well. I told you that a lot of times what will happen is that the slow step will have intermediates. Like every reaction has multiple steps. So if the second one is the slow step, that means rate is dependent on BR concentration and NO concentration. It depends on these two things. But then you realize that BR was made in the previous step, and BR's concentration itself is dependent on NO and BR2 concentration, because if these two have higher concentration, then BR will have higher concentration. So when we say that rate depends on BR's concentration because it's involved in the slow step, what we mean is that it indirectly depends on the concentration of NO and BR2 on these two things, because they are the ones that end up producing this BR, which then is involved in the slow step. So in that way, NO appears twice in your rate expression. And in that way, NO becomes squared. That means a rate is very sensitive on with respect to NO. And BR2 has order 1. So we did lots of examples of order 2 and 1 as well. TK, is this the previous one? Is this all clear?
Yes, sir.
TK, Minahil, Abdullah, is this clear? Aruba, is this clear? So the next part is there are other methods of determining the order of the reaction. And the other one was the half-life method. The half-life method was that if you've got two reactants reacting with each other, so that means rate depends on reactant number 1, A, and also reactant B as well. We don't know what the order is, and we don't know what the order with respect to B is. The first thing is I need to, like, if I'm investigating A, I need to make rate independent of B. I need B to be constant. Now it's very hard to keep B constant because when a reaction happens, B is also reacting and its concentration is also changing. So B will be affecting the rate of reaction. So the only way B's concentration becomes constant is that if you add it in large excess. You add so much of B that even if a slight amount gets used up, the quantity of B remains kind of unchanged. Like if you have 2000 moles of B and 2 moles get used up, then the amount of B and the concentration of B hardly changes. So if you want to keep anything constant, you just put it in large excess. So when the reaction is going on, its concentration hardly or barely changes. So that way you can eliminate one of the reactors. The rate would no longer be dependent on that because its concentration barely changes. Okay. Is this clear as well? So Ethan, is this clear?
Yes.
So I told you that as the reaction proceeds, A's concentration will decrease and it will eventually go to 0. The reason it's going to go to 0 is because I mean it's going to get used up and it's going to turn into C. So A's concentration would be maximum at the start, and then it's going to drop to 0. If the rate is order 0 with respect to A's concentration, then the speed with which A is decreasing with respect to time, which is the gradient. Remember, the gradient of the change that's happening, that's rate. So the speed with which it's decreasing, that would remain constant. And because if A decreases, the rate is unaffected by that. It has 0 order. The second one was that a rate could have order 1 with respect to A's concentration. That means if A decreases, the A's concentration would decrease because it gets used up. The reaction will slow down. If A decreases even more, the reaction slows down even more. So it's a direct proportionality. So the gradient kind of becomes lesser and lesser. Initially, the A concentration is high, so the reaction is fast. But then A's concentration decreases, so the reaction kind of slows down. This curve becomes less steep. It slows down even further. And as A's concentration touches 0, the reaction slows down further and further. Eventually, it's going to become a straight line. As A's concentration continues to decrease, the rate of the reaction would eventually, or the gradient of the reaction of this curve would go to 0. And in this case, we talked about the half-life, that the half-life remains constant, like the time taken for the concentration of A to decrease by half. The time taken for the concentration of A to decrease by half again and again. So the half-life remains constant. Is that clear? Lubena, is this clear? Zoha, is this clear?
Yes, sir.
Yes, sir.
Now the third one is K if it's order 2. Now, order 2 means, if it's order 2, that means rate is very sensitive to A's concentration. Okay, the effect on A's concentration, on the rate of the reaction would be a lot. Like if A's concentration decreases by half, right? So if A's concentration decreases by half, then that indicates that rate would become 1/4. So that means the rate is very sensitive to A's concentration. And so the graph would kind of look like this. I'm going to draw the boxes first, which would represent the half-life. Every half-life would double. Like if I'm starting at this point, this is A's concentration at the start at time t is equal to 0. So this over here is time t is equal to 0, and the reaction, the solution has a lot of A, and it will start to decrease. So it's going to become half. That's the first order. So let's say it decreases to half, and that's first order. Then it decreases to half again, and this time the half-life is double because the reaction is slowing down. So it's going to take a longer and longer time. So the time is increasing now. The third one is it now decreases to half again. And the fourth time is that it decreases to half again, and this time, one second, and this time it's going to be even, it's going to take an even longer time. So this is what the curve would look like. I'm going to just join these points. Take it very carefully, just a second. So initially the rate of the reaction is really, really fast, but then it slows down. And then it slows down even further. It takes a longer and longer time for A's concentration to decrease by half. And then, so even further, so it's continuously slowing down. And let me just, so it's constantly slowing down. And every time the half-life, it becomes double of the previous half-life. So every successive half-life is double of the previous half-life. Because this is what we learned over here. That rate is very sensitive to A's concentration. Like if A's concentration decreases by 1/3, the rate would decrease by 1/9. It's a quadratic relationship. If rate becomes 1/10, sorry, the concentration of A becomes 1/10, a rate would become 1/100. It would decrease by 100 times. So it's going to slow down and it's going to take a longer and longer time to finish. As A's concentration drops, the time required for the reaction to finish, it's going to just keep on stretching. And it's going to take longer and longer time. Every half-life would be double the previous half-life. Every time A's concentration decreases, the reaction slows down by a lot. Is this clear, everyone?
Yes, sir.
Yes.
Okay. So remember the three graphs that you can obtain. I mean, it depends on what the order is with respect to A. Either it's not dependent on A at all. That means the speed with which the reaction is happening, it just goes on at the same speed. It doesn't slow down. A is getting used up. The reactant is getting used up, but the reaction is not slowing down. So it's a straight line. It's very easy to identify order 0. You don't even have to measure the half-life. If you get a straight line, that's order 0. The only confusion would be in order 1 and order 2. In order 1, remember the half-lives are going to be constant. So the slowing down is not that much. The curve is slowing, but gradually. It's proportionally slowing down. A concentration keeps dropping in the reaction. The rate of the reaction slows down proportionally. But over here, the gradient changes a lot. Like A's concentration decreases, the rate of the reaction or the time required, it keeps on stretching. It takes longer and longer time. The reaction slows down by a lot. So you're going to look out for these three graphs. And also remember that every reaction has a lot of reactants. So if you want to exclude the other reactants from the rate equation, you need to make their concentration constant throughout the reaction. And the way to do that is you put them in large excess. That's something that's important, that they should be in very large excess so that their concentration almost becomes constant. And if they become constant, then they will not affect the rate of the reaction. So the rate or the gradient of the reaction will purely be dependent on A's concentration. As is this point, is this one clear to everyone?
Yes, sir.
Okay, Mirail, is this clear? Zoha, Sohail, is this clear?
Yes, sir. Yes, sir.
Actually, now, so that's one other method. Okay, so we've done two methods. One is that if you know the mechanism, then you can figure out the order. The second one is if you end up plotting the graph of the reactants and see how the concentration changes during the reaction. If you can compare the three graphs, half-life is constant, half-life doubles, getting a straight line, you'll figure out the order of the reactant. And then there's a third method. The third method is, I mean, it doesn't have a name. I'll call it the experimental method. So experimental method of finding the, experimental method for finding order. Now, this method is the simplest one. This is the one that's actually used because most of the time you don't know what the mechanism is. Like if I tell you that H2 and O2 are reacting to form water, I know the reaction, but I don't know what the mechanism is. Similarly, it's kind of hard to actually plot these graphs as well. Like if there's a reaction happening, for example, I mean, this one is also kind of impractical. It's pretty hard to actually plot this graph. One example is like if you have NaOH and HCl reacting together, right? You start the stopwatch and the reaction kicks off. So NaOH and HCl are reacting. Now the problem would be, how can you measure the concentration with respect to time in real time? Like if this reaction happens, like probably it takes 20 seconds. How can you measure the concentration of NaOH at every second? How could you measure the change in concentration of HCl at every second and simultaneously plot a graph and then figure out how the concentration of NaOH is changing during the reaction? Like you would have to like really stop the reaction a lot. And it would be kind of impossible to, and if the reaction is happening very fast, like in 3 seconds, the reaction is over. So you can't really like plot or measure the concentration of NaOH every 0.2 seconds or 0.5 seconds. So the point is, these two, the first two methods are kind of not that practical. Like if you're in the lab, you're standing in the lab, you'll use this method, which is the experimental method for finding the order of reaction. So all you need to do is, here's a reactant and here's your product, right? So all that you have to do now in this reaction is you change the concentration, right? Let's say I'm going to do an experiment. I'm just going to do 2 experiments. Let's say I double the concentration of R and I see whether the reaction speeds up or not. So no change in speed. The reaction takes the same amount of time. So that means it's order 0. If I double the concentration of my reactant and the rate doubles as well. How do I know the rate doubles? Remember, rate is inversely proportional to time. Like if the rate doubles, the time taken would be half. Like if one reaction takes 100 seconds, the other one takes 50 seconds, then the 50-second one is twice the speed of the 100-second one. So rate doubles. So that means it's directly proportional. That's order 1. And similarly, if the rate becomes 4 times, like if I double the concentration of my reactant and the rate, if it was taking 100 seconds, now it's taking 25 seconds. So that means the rate has increased 4 times. So that would be order 2. Now it's kind of simple, but you have to take care of a lot of things. But the experiment is simple. Like you just want to find the order, right? You just alter the concentration of one of the reactants, see what effect would that have on the speed of the reaction. If there is no effect, then that means rate is not dependent on that particular reactant and so on. Okay? Is this point clear? This one?
Yes, sir.
Yes, sir.
Achha, but when you try to do this, you would have to be very careful about a lot of things. Okay? The first thing is, the very first thing. So I'm going to do an experiment, right? The first thing is we need to define what rate is. Now, technically, rate is the change in concentration with respect to time. Okay, so it's how quickly the concentration of something is changing with respect to time. So for example, I have this reaction. I've got 2 NaOH reacting with H2SO4, and it produces Na2SO4 and 2 water molecules. Now, when a reaction happens, the first thing, and the unit for rate is mole per dm cube per second. Like change in concentration with respect to time. So it's mole per dm cube per second. That's the unit. Now we'll encounter a few problems. The first one is, whose concentration are we talking about? Like, you've got lots of things there. So if I say that the rate of this particular reaction is, I mean, I need to find the change in concentration with respect to time. So whose concentration are we talking about? So for example, every second, NaOH 0.1 mole per dm cube NaOH gets used up. Per dm cube per second gets used up. So the change is negative, like it's going to be a negative change because the gradient would be negative, NaOH would be decreasing. Now, according to this, can you even tell me if every second 0.1 mole per dm cube is getting used up, how much H2SO4 would be getting used up every second? Any idea? Anyone?
0.05.
Okay, so it's going to be 0.05 because it's 2:1, right? So the point is that change in concentration with respect to time, I mean, you're talking about the same reaction, right? But if you say that the rate of this reaction is changing concentration with respect to time, if I choose another reactant, I'm going to get a different value because the mole ratio is different. That reactant would be decreasing with a different value or different rate. So it would be decreasing at 0.05 mole per dm cube per second. And similarly, Na2SO4 would be increasing. Its change would be increasing. It would be increasing at it would be, it's 1:1. Every time one reacts, one is produced. So it would be increasing at 0.05 mole per dm cube per second. And the last one is water, that would be increasing at a rate of 0.1 mole per dm cube per second. So when I say that I want to measure the rate of the reaction, and I say that rate is concentration with respect to time, so whose concentration are we talking about in the first place? Okay, that's the first problem. Like, what is the rate of the reaction? Is it this one? Is it this one? Is it this one? Or is it this one? And when it comes to the reactants, the change is decreasing. So it has a negative value because it's always decreasing. They're getting used up. And when it comes to products, the change in concentration has a positive value because it's increasing. So the first thing is, when we talk about rate, we're talking about the molecule which has the simplest, I mean, the one that has the coefficient of 1. We're talking about that one. It's this one, right? Or we can have this one. Okay, so the first thing is, when we talk about rate, we're going to find the concentration with respect to time, with the change in concentration with respect to time for the reactant that has coefficient 1. But if you're using this one, you can make this coefficient 1. What you can do is you can take this and divide it by the coefficient, which is 2. So if you divide this by 2, you get the same value. And if you take this, you can convert this into coefficient 1. You take the rate and you divide that by 2 as well. Is this clear?
Yes, sir.
Okay, so the problem was that when you measure the rate, its concentration with respect to time, but the equation has different mole ratios. So every reactant would, its concentration would be changing at a different rate. And when you try to measure rate, you always measure it with respect to the one that has coefficient 1. And if you're not doing that, you can make the other ones as coefficient 1 by simply dividing the rate that you get by the coefficient that's in the equation, which is 2 in this case. You'll get the same value. All 4 would be the same value. And you can ignore the sign. I mean, the sign is irrelevant because remember, the speed is the change that's happening. We don't care whether the change is negative or whether the change is positive. We're just measuring the change with respect to time. So we're talking about the scalar value, not the direction. So it's so when you talk about rate, you're just talking about the scalar value. So ignore the negative or positive signs. Whether it's increasing or whether it's decreasing doesn't really matter. Is this clear?
Yes. Yeah.
Okay, so I'm just going to add this over here that divide by coefficient. So every time, no matter what reactant or product you choose, you get the same rate. The second one is ignore the sign, simply ignore the sign. But then there's a bigger problem here, and that is that the graph, let's say for NaOH, okay, let's focus on NaOH. It's not going to have a fixed rate value. No reaction has a fixed rate value. The rate of the reaction constantly changes with time. Okay, so if I plot the concentration of NaOH with respect to time, what's going to be happening is that the reaction would be really fast at the beginning. Most reactions are usually fast at the beginning, but then they sort of kind of slow down. Okay, most reactions have this curve with respect to time. So the problem is that even if I measure the concentration, like at what time am I measuring it? Because over time, the reactions would always slow down. So when I talk about the rate of the reaction of a particular reaction, it keeps on changing with respect to time. So right at the beginning, the reaction is kind of really, really fast. So the gradient is very steep. So the starting gradient is very steep, then the gradient becomes lesser and lesser. And then eventually it's going to go to 0 because the reaction would stop. It's going to become a straight line. Okay, is this point clear as well, that we have an issue, like at what time are we measuring the rate? Is this clear?
Yes, sir.
Yes, sir.
So the thing that you do is another thing about when you try to measure the concentration with respect to time, you always look at the rate right at the beginning. I mean, not after 2 hours, because after 2 hours, all reaction will stop. Not after 20 seconds. I mean, it's always going to be at 0 seconds. Make the gradient, once you have the curve, make the gradient right at the beginning. Okay, so another very important point is that time is an issue. So always initial rates are measured. Like right at the beginning, like how fast was the reaction right at the start? Like for example, if you pour Coke in a glass, like Pepsi in a glass, and bubbles start forming, we're just interested in the change that's happening right at the beginning, not after like 20 seconds when the bubbles start dying down. So always the initial rate of reaction is compared and measured. So that is also, so it's always going to be a comparison of initial rates. Then there's another issue, and that issue I've already discussed. Like, how can you kind of measure concentration with respect to time? That's a pretty difficult thing to do. Like if you have a beaker, like if there's a titration going on, right? Or maybe there's a reaction of Mg with HCl. And let me show you. So this one. So there's an Mg and HCl reaction going on. So, I mean, in the laboratory, how can you in real time, like every 2 seconds or every 5 seconds, measure how the concentration of HCl is changing in this test tube? That's kind of a very tough thing to do. So what you also do is, in the laboratory especially, what you're going to do is, instead of using concentration with respect to time, what you can do is, I mean, we know that rate is concentration with respect to time, or the change in concentration with respect to time. So what we're going to do is, we're simply not going to measure concentration. I mean, that's the change. What we're going to do is, if you're going to do comparison, you keep the change constant. I mean, whatever the change is with respect to time, change in concentration with respect to time, it has to be a constant change, and your rate would become inversely proportional to time. I mean, this is what, like if there's a 100-meter race, no one is measuring meters per second for every runner, right? You just want to know who's fast and who's slow, right? That's what we are in the lab. That's what we are trying to measure. So what they do is, they don't measure the distance and then they divide by the time and they take meters per second. What they do is they keep the distance constant. Like the speed is distance over time, right? It's the change with respect to time. It could be change in concentration with respect to time. Technically, it is the change in concentration with respect to time. But like in a 100-meter race, you've got the distance is fixed. So what are the officials measuring? They're only measuring time. That's it. You don't have to actually measure the concentration. Is this point clear?
Yes, sir.
Okay. But the only thing is that if you're comparing a reaction, you have to ensure that your starting point and your end point are fixed. Okay, just like the 100-meter race. I mean, it won't make sense. I mean, the times won't make sense if different runners are running different distances. Like if one runner is running 100 meters and the other one is running 200 meters, and you're trying to compare their times, I mean, that won't make sense. So the change has to be constant. I mean, this change over here, you have to ensure that that particular change is fixed. That's not changing. And that change could be anything. Like if you just look at the reaction, I mean, this reaction over here, you just need to have a starting point and you need to have an end point, just like a 100-meter race. There's got to be a starting point. There's got to be an end point. And if you're trying to do comparisons, then all the comparisons must follow the same starting point and the same end point. So you're doing this experiment, right? So what could be an end point for this? Can you decide, like the reactions are running races? So what could be the end mark? I mean, one of them that comes to my mind is that the Mg completely gets dissolved. So I'm going to stop the stopwatch when the Mg gets completely dissolved. If the reaction is slow, it's going to take a long time. If the reaction is fast, it's going to dissolve very quickly. Is this point clear?
Yes. Yes.
Okay, so for every reaction, you have to kind of figure out what the change is. What's the starting? I mean, the starting point is easy. Like starting point is when you mix everything up. That's your starting point. That's when the race starts. The end point is when do you stop all the reactions? Like when do you stop the stopwatch? So I'm going to pick this reaction first. The Mg plus HCl reaction. And we're going to imagine that we are in the lab and there's H2 gas bubbles being formed. So lots of apparatuses could be used, lots of different ways. This one's a gas collection apparatus. So what I can do is I can kind of use this one. So I'll just copy this one. As this is one thing I can do. I can add Mg and I can add Mg to HCl. So imagine this is mg. I mean, there's a bottle of mg in the test tube over here, and there's HCl. I added mg to HCl, and all of a sudden this H2 gas bubbles are formed. So that's my starting point. My stopwatch is on now. I'm going to put a mark over here. And I'm going to say, this is the time when I'm going to stop the stopwatch. And I'm going to see the reactions. They will be sprinting, and I'll just see who gets to fill this H2 gas, fill this up till this point as quickly as possible. So I'm just going to measure the time. Is this clear?
Yes,
Yeah.
sir.
So plus you can do a lot of other things as well. You can, I mean, there are lots of other things. We're going to discuss all of those things, TK, in the next class. Just remember for now, when you're doing experiments, you always measure the initial rate, because all reactions, their rate keeps changing with time. They slow down. So always initial rates are measured, and a rate is the change in concentration with respect to time. But what I'm going to do is I'm just going to ignore concentration. I'm just going to keep the change constant. That's one thing. And what I'm going to do in the lab is I'm just going to measure rate is inversely proportional to time. That's it. As long as the change is constant, I have to keep the change constant. So let's continue tomorrow then. Okay, everyone. Take care, Allah Hafiz.